Okay, I am starting another series of podcasts. These don't amount really to a full course, but they are excellent short courses or a really good introduction to the topic, like the monsoon extremes or the cyclones and so on. The subseasonal to seasonal forecasts, all these were carbon cycle. You can think of them as primers or introductions, whatever we want. But here I'm going to focus on intraseasonal timescales. I think you already know that this includes mostly the so-called monsoon interseasonal oscillations, which we repeatedly mentioned in the monsoon extremes, in the tropical dynamics course, and various other places, including S2S forecasts, and also MJOs, the Madden-Julian oscillations. I'm not going to go too much into West African, South American interseasonal oscillations. I'll cover MJOs and MESOs and some parts of the oceans, air-sea interactions, etc. Okay, so let's start with this chapter, but first, this is coming from a book called Interseasonal Variability in the Atmosphere Ocean Climate System by Bill Lau and Dwayne Walliser, two good friends. I've worked with Dwayne for a long time. This is the second edition of the book. The first edition came out in 2005. This one came out in 2012. The book opens with a historical perspective by Roland Madden and Paul Julian, who are, of course, most well known for their original report on the interseasonal oscillations they discovered in various data. There is a Chinese paper now which reports that maybe a decade or so earlier, the Chinese scientists had also looked at some specific aspects of interseasonal oscillation, which are essentially part of the so-called Madden-Julian oscillations, which the name has stuck now, but nonetheless history is full of such co-discoveries that happen in different places, and one team gets credit because the other one doesn't get publicized outside, and so on and so forth. But the canonical figure, the seminal figure that Madden-Julian put together as a schematic is this one, which is showing the longitudes here from the African sector into the Indian Ocean, the maritime continent, West Pacific, going into the Eastern Pacific and the Atlantic sectors. And the lettering here, it says A, B, C, D, E, F, G, H, but we are starting here in the Western Indian Ocean, where the genesis of Madden-Julian oscillations typically happens, and the system moves, the convective systems move systematically eastward. There are details about what happens when they approach the maritime continent, whether they get weakened, stalled, they detour southward, or they cross and continue on the western side, and so on and so forth. But without spending too much time, because we will come back to this, we are looking at a convective origin of a convective system here on the Western Indian Ocean. There is the tropopause that's being shown in the in each of these, which are separated by about 5 to 8 days, 8 to 10 days, so pentad to a couple of pentads approximately. And you have low pressure just behind the convective system, convergence, rising motion, low sea level pressure as you expect. So convergence at the lower column of the atmosphere and divergence at the top, and you have these kind of other cells that are associated with this intraseasonal timescale. You have to be careful. So as the system moves eastward, you can see the sea level pressure getting ahead of it as a Kelvin wave, and behind that there are Rossby wave signals, which we will come back to later on. And you can see that the system keeps moving eastward, and the sea level pressure signal propagates further out, and the scales of these convergence and divergence cells are also related to these waves and so on. So The convection tends to die once it gets to the Western Pacific, because as it goes east of the dateline, the sea surface temperatures drop below the convective threshold, so convection is often not found. So you can see the weakening of the convection over here, and basically disappears as it crosses South America into the Atlantic sector. And there are so-called primary MJOs which originate here, and secondary MJOs which are considered reborn from the signature of a previous MJO that probably circumnavigated, and so on and so forth. So for historical perspective, I'm including this, but we'll come back to MJOs later on. Quickly moving to the South Asian monsoon, the chapter by B.N. Goswami. We'll start by looking at the South Asian summer monsoon and active break cycles. So looking at the climatological mean precipitation based on a product called CMAP, which you can look up. There are several products, climatological monsoon map, whatever, the rainfall product. There is GPCP and so on and so forth. This is being shown for boreal winter, so December, January, February, and summer, June, July, August, September. So the monsoon onset typically happens at the end of May, beginning of June. The withdrawal happens around third week of September to end of September, which is changing with global warming and so on and so forth, which we have talked about when we talked about the monsoon before. We will see next the winds at 850 hectopascal, so at the boundary layer level from NCEP reanalysis, and also from the 200 hectopascal level. There are many details here. So looking at the precipitation in the DJF, sun is to the south, the ITCZ or the intertropical convergence zone over the Indian Ocean is to the south. The rainfall scales are larger. Indian Ocean is a warm ocean, as we will see, so the ITCZ structure is not as narrow and tight as it is over the Atlantic and Pacific sector, especially the Pacific sector. Plus there is the Indo-Pacific warm pool, which is very warm. Maritime continent is the boiler box, as named by Ramage back in the 1960s. And the other thing is, in the summer monsoon season, you can see that there is still the convergence zone and the ITCZ over the ocean, because the warm sea surface temperatures hold on to the marine ITCZ, and there is the extension of rainfall into the monsoon domain over the core monsoon zone, with a peak over here west of the Western Ghats, which is the orography running north-south here. Himalayas are up here, Burmese mountains are down here, and this is the strong convection center over the Bay of Bengal, which is very warm as well. And you can see that this has a large scale southeast northwest structure, which appears in the pressure as well, and there are systems propagating across here at quasi bi-weekly or 10 to 20 day time scales, and there are 30 to 60 day time scale systems propagating northeastward here. These are northwestward, and so on and so forth. Okay, so we'll come to those sorts of details, but the net effect of these kind of intraseasonal oscillations, you can call them, is that you end up with so-called active and break periods over the monsoon domain, where there are weeks where rainfall is above the seasonal daily mean, let's say, daily climatology, and below that envelope, as we will see in a minute. So the 850 hectopascal winds in DJF are going from the continent north east to southwest. Basically sun is to the south, so the ocean is warming, lower pressure, land has got lower heat capacity, winter, high pressure, so you add Coriolis, you end up with these sorts of winds, with the wind speeds shown here in colors, and you can see the easterlies extending here, and then the winds change directions as they cross the equator, and over the maritime continent they almost become south westerlies. So there is year-long rainfall over here, as you can see. Rainfall occurs here, but this is the drier season as the ITCZ moves north with the sun, especially over this side, and this is the wetter season, and so on. And the south, the monsoon season is known for its strong trade wind regime that here exists here throughout the year, and then merges with the south westerlies crossing the equator, bringing lots of moisture with it. Some of the strongest surface westerlies in the tropics occurring crossing over the Western Ghats over to India, bringing moisture, also crossing over here into the Bay of Bengal, curving around and creating the cyclonic circulation. And at 200 hectopascal, you can see that in the boreal winter season, the mid-latitude westerlies extend way south into the tropics here, but once the summer monsoon gets set in, the westerlies get pushed to the northern latitudes here north of India, and you get the easterlies getting set up, easterly jet in the upper atmosphere at 200 hectopascal with fairly strong wind speeds as well, and the westerly maximum is up here. So massive changes happen, and you can see the southwesterlies here. The southwesterly jet has obviously a strong barotropic structure going all the way from lower levels to the upper level here. Sorry, should be careful. This is the DJF. So you have northeasterlies near the surface, southwesterlies in the upper atmosphere. And on the other hand, you have southwesterlies near the surface and easterlies and westerlies here in the upper level, with the northeasterlies at the upper level being further south here. Be careful, I said it a little bit wrong. Okay, the active break periods are shown here, looking at different years. So 1972, 94, and 2002. We'll come back to this later on, that the climatological envelope is shown here of cumulative rainfall, which is the same for each year. So during a strong El Nino year, you have fewer active periods and more longer break periods. So the average rainfall is below normal. And this is a slightly wet year, so more active periods, shorter with fewer break periods and higher amount of rainfall. This was basically a wet year. This was another drought year with a El Nino, with the warming located around the dateline, so-called Central Pacific or dateline El Nino. And you can see here, you can see here that here again you have longer break periods with fewer shorter active periods, with rainfall being even lower than 1972, way below normal at 642.331 millimeter. The average is around 900 millimeter, 890 millimeter or so when averaged over June, July, August, September for the All India monsoon. Whereas this is the averaging region shown here. So that's the basic intrinsic time scale in the monsoon, the active break periods or intraseasonal time scales. And we will keep looking at the details from this chapter before we go on to look at the air-sea interactions, ocean parts of the summer interseasonal variability, and then we'll come back to MJOs during the boreal winter season or October to April period. Okay, so this is a good start for this series of lectures. So I will stop here and come back to further details in the coming podcasts.